Now we have Patrick Ball from the Human Rights Data Analysis Group. Thanks, Patrick.
Thank you. Data's always lying. And here's some data, and I'm going to tell you how it's lying. So I get to show the first graph of the conference. I find that very exciting. And I also get to talk about the first concrete algorithm. This is a really tricky one. We're going to draw a line through the points. We're going to draw a line through the points. It's going to be transformative. We're going to use someone's height to predict their weight. It's pretty exciting stuff. Now, this brings up the notion of data. And here's a bunch of data. I found it online. It's very big data. Very, very big. Very, very big. Hundreds of thousands of people combined height and weight measurements that I plotted a line through. And that gives us a way to understand what we mean by a model. The training data plus the algorithm gives us a model. And in this case, we have a trivial model that we can describe in 7th grade algebra, that weight equals minus 122.6 plus 3.5 times someone's height in inches gives you their weight in pounds. Now, this is a great model, and I'm going to show you how great it is by showing you a line drawn through points that I didn't show the model beforehand. And look at that line, it goes right through those points. Will someone please call Wired Magazine this minute? We are displacing the entire industry of scales. We are transforming fashion, fitness. All right, calm down. This is called an out-of-sample prediction, and it is considered by most machine learning practitioners the way you test the model. You've got data that you didn't show the model, you put your algorithm, let your model draw the line through it, and you see how good a fit you've got. And this notion of it being a quality control measure is both completely correct, it's accurate, but it's also absurdly optimistic. It's absurdly optimistic because we randomly drew these points from the same data set we used to train the model. And here's where it all gets really tricky. Because, oops, what about those guys? Well, it turns out, shoot, I'm really sorry, forgot to tell you. The data I trained the model on was of Hong Kong school children. And these red points are Major League Baseball players. Turns out, not the same. Turns out, I could have used a different model. But because I didn't know that, because I didn't get out of my chair and go and look at the data in the real world, I just took a data set that came to me by some automated data generation mechanism, I felt really good about my model. And I just made claims about it. And not only did I make claims about it, if I made sufficiently powerful claims, people may have made policy on that basis. And we would have kind of blown it for all these other people. So, how bad can it be, right? Maybe we just put a caveat on it. We say, no, don't worry about it. Can't be that bad. No, it actually wasn't even all that great a model for the Hong Kong school children, because it turns out that when you ask people to opt into a study, people who love their weight and are really happy about it opt right in and hop up on the scale, and you get the blue dots and you draw a line through them. People who are self-conscious about their weight opt out. And so you get a whole cloud of people who you don't observe. And now you have a model that's really for not just Hong Kong school children, but the fit and thinner Hong Kong school children, not for everybody else. So what is this model doing? Well, the model is telling us the relationship among the variables we can observe and that we have observed. It is not telling us other things. So what are the points that were unlikely to be observed? What did we miss? And are we selling ourselves, or is the proponent of this model selling us a caveat fantasy? And I sometimes go back and forth, is it a fantasy? Well, that's the self-delusion part. Is it a fallacy when we're selling it to someone else? This is the fallacy in which we say, well, our model only applies to this part of the world, as though we know what that subpart is. Whenever someone says, well, okay, our model doesn't do that, but it does this, how do we actually even know it does that? How can we define that if we don't know what we're missing in the training data? If we don't know what the data excludes, we don't know what the caveat should be. And by the way, does anyone even remember their caveat by the time they get to the conclusion? No, it's only on the first page. By the time you get to the end of the page, we're selling it as though we were pitching a Wired Magazine reporter. So we all have to use these things, but we should be very, very careful about their limitations. And finally, this was mentioned in a couple of the previous talks, and I think it's worth highlighting. Is there a feedback loop between the process of observation and the way the model works? Does the model then teach us something that we then use to take some action which generates new data that we put back into the model? This is particularly problematic, I think, in predictive policing and risk-based modeling in criminal justice context. My colleagues and I have a couple of studies about this, but it occurs in a number of other areas as well, and Kathy's done a bunch of work on this as well. It's really important. How do these feedback loops then distort what we understand from the model itself? And so let me leave you with some conclusions. let's stop talking about algorithms and talk about models, because once we talk about models, we enable the conversation about the data that trained the model. All algorithms in the same kind of classification are going to do essentially the same thing. Let's not worry about that. And so let's also stop talking about big data, because big data that's not necessarily more representative actually tends to increase our certainty in the wrong answers. Thank you.
Thank you so much, Patrick.